today we're talk about what is a power spectrum, and we'll cover a few other aspects of that and various aspects and representation of the power spectrum. So you can represent them, you plot them differently. And then after that, we'll finish off with a case study. So to show you where, how you can apply it, where I use it, and it can be a very powerful tool. So Fourier, really, who was this man? Jean-Baptiste-Joseph Fourier, 1822, showed that actually, any kind of function could be rewritten as a accumulation of an infinite sum of harmonics. And so if you imagine here, if you got this one cycle and I have the second cycle of different frequency and another cycle of different frequency, if I were to add them all up, this is what it would look like. And this is when we look at this, we're in the time domain. We're in the time domain, in the time dimension. Now, if we were to look at it from the frequency domain, we would see the strength of all those three cycles. We would take this series here, do a Fourier transform, and would actually break it down as to its fundamental harmonics. And that's known as the frequency domain. And so we're looking at the data differently. So let's talk about the Fourier series of a square wave. I know you could see here that certainly is a lot of squiggly lines. So if I were to zoom in, there's a square wave right there. So if I were then to try to reproduce that square wave using Fourier series, I would use this series right here. So for a square wave, and it's different for a triangular wave and so forth and so forth, but for a square wave, you use the odd harmonics. So you got your base harmonic at 1, and then you got three times faster for the second harmonic, 5 times, 7 times, 9 times, and so forth. And not only that, you would actually take the inverse of the amplitude. And that would then, if you add up all those harmonics infinitely, you would reproduce a square wave. So let's take a quick live demo here, and I'll show you what I mean. So I've actually built this. So what you're seeing here on the left-hand side is a sum of all the of two sine waves I've activated here. Your base harmonic on the left-hand side, you see on the right-hand side, you see the red line. That's your base harmonic, and I've added the second harmonic, which is 1/3 the amplitude and 3 times faster. So if I were to then actually add other harmonics here, I'm going to add them all up. I'm not going to spend too much time because it does take a fair bit of time to actually see that, and maybe we come back to it at the end. But now you can see I'm actually activated the rest of the harmonics, and now we should start seeing more of a square wave. And I don't want to have too much dead time here to be able to see it. So perhaps we can actually see it later on, come back to it. But you will see that it's actually going to look more and more, not perfectly, because obviously we don't have an infinite number of series of harmonics here, but it is going to happen. So you can see all these here all get added up to form this cycle right here. So I will kind of minimize this for now. So as a matter of fact, so if I were to show you, not in real time, but there's the base harmonic. This is where I added the second harmonic. This is where I added the third harmonic. So you can start seeing here that it's starting to look more and more like a square wave. There's the fourth harmonic. There's the fifth harmonic. And for some reason, I didn't add the sixth harmonic there. So obviously, you can see it's starting to look more and more like a square wave. So when we do a power spectrum analysis, there are two ways of calculating. There's probably more than two ways, but two ways that I know of that I actually use the Fourier transform. One's called the fast Fourier transform, FFT, and one's called the full Fourier transform. So what's the difference here? The fast Fourier transform requires a power to 2 to the n power number of samples. So if I were to have, so that means I can go up to, let's say, 65,536, which is 2 to the power of 16 number of samples. Obviously, I can go more. But if I were to have only 65,535 samples, the FFT algorithm would only use the first 32,768, which is 2 to the power of 15. I would lose a lot of information. So if I have an oddball number of samples, I might want to use the full Fourier transform. So everything has a price, right? I've always said that everything has a price. And so why don't I use the full Fourier all the time? Because it is a very, very computationally very intensive. If I were to do a fast Fourier on 65,536 samples, it would take a fraction of a second. If I were to do the full Fourier on the same amount of samples, it would take probably 10, maybe 15 seconds, depending on your computer, even with today's computer. I remember doing this on almost 30 years ago on, for those of you may know, on a 386 Intel processor. And it would take maybe up to 5 minutes before we could actually spit out the full Fourier transform. Yes, I am dating myself there. So what does a Fourier transform look like? So you can see here, this is a full Fourier because I actually had an oddball number of samples. So I use a full Fourier. So what you see on the y-axis is the contribution of each harmonics to the total variance of the signal. You can see there are peaks here, there. These are all the harmonics. So I'm going to erase all that. These are all the individual harmonics, all equally spaced. Now, the blue line, what you see is the integral of the power spectrum and the total contribution of each harmonic to the total variance. Now, some of you may remember Parseval's theorem saying that each harmonic, all added up, will end up equaling to the variance of the signal. And the variance is sigma squared, not to get too technical here, which is related to sigma, which is related to the 2 sigma. So you can see here at the bottom end, this is linear frequency. Linear frequency. So before I continue on, one thing I want to go back to. Here I sample this once a second. So this signal here was sampled at 1 hertz 1 second. Nyquist or Shannon's law says the fastest frequency you can reproduce has to be twice as slow as the fast sampling frequency. So if I sample at once a second, that means the fastest cycle I can reproduce is 0.5 hertz or 2 seconds per cycle. Remember, period, frequency. And that's going to be a recurring theme here. And some of you may know, like reliability to vibration analysis, we talk in hertz. In process control, we tend to talk about seconds per cycle. And I'll touch on that later on. So as I said, Shannon's law says the fastest frequency I can reproduce has to be twice as slow as the sampling frequency. So what happens if that does not have that is not the case? So here I got a pretty fast cycle here, and suppose I were to sample it a lot slower. So you can see the yellow line is not really a true representation of what the actual signal is. So once I start sampling slower and slower, I'm actually losing any kind of resolution on the actual data. And if I sample a lot slower, that representation has nothing to do with reality. It is a ghost. And that means that signal has been aliased. So if you think we all have process data historians, and a lot of these historians will sample once a minute. We got to be careful because what we're seeing in our historians being sampled at once a minute may not, the pattern we're seeing may not be actually the true pattern that's happening. So just a word of caution there. And how do we prevent this? What we need to do is that before we sample, we need to put this through an anti-aliasing filter. So if I got my signal coming in, I have to put it through an anti-aliasing filter, and of course I have the world's worst handwriting, prior to sampling the signal here. And it is essentially what it is a low pass filter that will attenuate the high frequency to reduce the chance of aliasing. At the analog input cards, there will be an anti-aliasing filter. An analog anti-aliasing filter could be an RC filter, either first order or second order, in order to prevent this aliasing from occurring. And anytime you subsample, so let's say you got a time series at 1 second per sample, but now you got your historian coming in once a minute and picking up a value, prior to that subsampling, the data should be put through an anti-aliasing filter. But that's just as a side note. So as I mentioned here, so you can see here, this is linear frequency. And it is actually the true way to actually plot a power spectrum. And you can see here, everything is spaced out equally in terms of frequencies. But if I tell you what is 0.003 hertz or 0.3 millihertz, that doesn't really tell you a heck of a lot, does it? Because in the world of process control, we talk about variability being in seconds per cycle, 10 seconds per cycle, 300 seconds per cycle, and so forth and so forth. So what I tend to do is I tend to plot it linear period, which is not linear period, but you can see here all the harmonics tend to crowd towards the right. But now these are seconds per cycle, as we're seeing here. So we are losing some resolution, but it's the same information, just plotted differently. So if I actually zoom in on that, you can see here, I got the same information, but now plotted differently. And you can see because of the inverse nature, the actual plots or harmonics appear to be much closer. So that's usually, like I said, because if you talk to vibration people, there'll be 30 hertz. They're talking about 30 hertz, 20 hertz, 100 hertz, 2 hertz. And in our world, we talk about 50 seconds per cycle. We talk about 76 seconds. We talk about 100 seconds. And that's why we operate in linear period. So before we do that, before I talk about that, let's go back to there we go. So you can see here, meanwhile, back at the ranch, talking about all the harmonics are all added. And you can see here, it's starting to look more and more like a square wave. So just as a side note again. So how do we use power spectrum? How do I use power spectrum? Be able to track down the source of variabilities. So here, this is did this actually, it was towards the end of last year, and I was working on a paper machine. It's a recycled paper mill. And I'll explain a bit more as we go along here, but recycling paper mill, what they do is they'll take your blue box paper and everything else, will sort it out, and then they'll put it through a pulper, break it back into fiber, and they make a pulp slurry called paper stock. You think of a paper mache, and they'll treat it, they'll clean it, take all the staples out, the sand out, the plastic out, and so forth, and then they'll put it back on the paper machine to make more paper. Here is making linerboard. And this machine actually has it's a 2-ply machine, so it actually has a top ply and the bottom ply. And eventually here, this goes to the paper machine. That goes to the paper machine here. So it's important here when you make paper that you got to get it right the first time, because if you have variability, if you have oscillations going on here, if you have oscillations here, once you make your paper, it is that variability is cemented in the paper. You can't, it's very, very difficult to undo. You can't put it into the tank, and sometimes you have to repulp it, which is costly. So here you got a machine chest, which is basically the last tank before you put it on the paper. It's level control. And you can imagine here, what we have here also is called consistency meters. And what consistency meters are, they will measure the amount of fiber and water in your pulp slurry. Very, very important to maintain a constant concentration of fiber going to your paper machine, because that will affect the quality of the paper itself. And you can see here, I have level control here and I have level control there. So if my level controller has some sort of issue, then my flow here could oscillate. That can cause then my consistency to oscillate as well. And that then can get transmitted through to the paper machine, affecting the quality of the paper. And actually inside here, I didn't really show it, but there's actually in between, there's actually very flow sensitive piece of equipment called refiners. And what a refiner is basically we're putting the pulp slurry between two counter rotating plates, and it fibrillates the fiber. Each paper fiber actually has little hairs. This fibrillates it, essentially giving it an afro. So when you put on the paper machine, all those fibrils will intertwine in making the paper stronger. So all this here to make sure we understand the process. So this is not the actual paper machine here, but this is what a paper machine looks like. And for those of you who've never seen it, right here is this called the head box, and it's spraying the water this way, a flat sheet of water onto the wire. The speed of the jet and the speed of the wire rotating have to be matched up very closely. Otherwise, it can affect the formation. That's the bottom ply. The top ply is over here going this way. And the two will meet right here, and off it goes. So this is an actual paper machine. So here's another schematic way of looking at it. So here's the top ply going this way and the bottom ply going this way. Paper making process goes through a press section. We squeeze the water out. So when you put the wire here, put the stock here, it will be about 99% water. And so the whole rest of the process after that is to dewater, to take the water out of the paper. So the first part we do is that we try to squeeze the water out of it by pressing it, kind of like putting a paper towel on trying to get the paper towel on out of trying to absorb it from there, and then squeezing the paper towel, get the water out. Then after that, it goes through a series of dryers, and these are the heat is generated by steam. Obviously, the higher the pressure, the steam, the hotter the dryer cans are, and eventually it'll end up here where there's a scanner. What does a scanner look like? A scanner looks like this. The actual paper would be going in between here and going this way. This scanner goes back and forth probably every between 30 to 40 seconds. It scans the paper. Inside this sensor head, there'll be multiple sensors. One is called a beta gauge. It's a nuclear gauge using typically Krypton 85, and that measures the basis weight. And basis weight is the weight of the paper, the fiber, and the moisture remaining. Typically at the end of this, when the paper is manufactured, at the end it's going to be around 5, 6, 7% moisture. And they can also another gauge that will actually measure the moisture itself. All that because, and moisture when you make linerboard is very, very important. So you can see here when you buy your box, you get your stuff from Amazon and it's in a box and it looks like this. The key here is that if the moisture profile on the top ply and the moisture profile on the bottom ply is not very, very close, one can dry out faster than the other and will end up causing the box to warp. And it's something the box manufacturers really do not like. So that's why moisture is very important in linerboard manufacturing. So when I went there, I was collecting data on the moisture. So this is data here over 48,000 seconds. So almost half a day's worth of data and percent moisture. And you can see here, clearly we could see oscillations here. And when we look at the power spectrum, you could see it was oscillating in the order of maybe around 1,000 seconds per cycle, give or take, maybe a bit slower than that. So I said, okay, I was hoping, all right, so what could be causing this? So I collected data then on the machine chest, the liner machine chest. If you remember, there are two tanks feeding that same paper machine. Now here I keyed in on the output, but because I was thinking that output then could actually, will be an indicator of the flow. I didn't have a flow measurement there. And as you could see, go back to here. As you can see, it is oscillating as well, but it did not line up with the moisture variability I was looking for. So I was kind of bummed out about that. And that is on the top, the liner machine chest. And then I looked at it on the filler machine chest. And once again, you could see that didn't line up either. So neither one of these variability that I was observing upstream of the paper machine were major contributors to the moisture variability. Let me go back here. You can see here this one probably lines up with that one, but not a huge contributor to the actual variability. So I was kind of bummed out. So then I said, okay, well, I'll look elsewhere then. So then I looked at one of the main steam headers. Remember, the dryers are fed steam. The steam obviously generates heat, and then the hotter the steam, the higher the pressure of the steam, the hotter it is. You get more drying, and the lower pressure, you get less drying. So right here, I took a look at this, and I could see that actually that my steam pressure was oscillating, and that lined up with the moisture variability I was looking at. So I was pretty excited about that. So then I was tracking down the source of the variability. Now, different the dryers are separated in different sections. So this is the 5th section. This is the last section here before we actually finish off making the paper. And that is under control from the supervisory control to adjust the steam pressure based on the measured moisture observed at the scanner. And you can see here that was oscillating. So everyone in the dryer section were all dancing at the same frequency, at the same period. And so therefore I said, okay, that is a major source of variability in my moisture, which is critical to manufacturing good quality paper. And so I did retune it. Now, there were other issues with this. There were some valve-related issues that are still being addressed right now. But as you can see here, as I retuned it right there, I eliminated that oscillation. And so therefore I was able to reduce that variability. And what is the end result of this? Is that up above here, this is the moisture data before. This is same scale here, same scaling, no trickeries. And you can see here that once we retuned it, that variability, that cycle was gone. And so this is how we use power spectrum to trace variability. It's a lot harder to do in the time domain because you just have to figure out does it line up? Does it not line up? The power spectrum will tell you the truth, whether there is an actual cause and effect by observing individual power spectrums and comparing them. And that's pretty much it. It's always a little bit quicker than I think it's going to be. Next month, we're going to be continuing on the frequency domain. We're going to talk about the frequency response of a PID controller. We think that a PID controller controls. Well, does it? It can control certain things. It won't be able to do other things. And in between, it might actually make things worse as well. So you're more than welcome to I hope you certainly will sign up for that. And then I will actually open it up for questions. And as I mentioned, there is a 10-second time delay. And I hope I didn't go too fast. If I went too fast, let me know. We can go back and answer any questions you may have, anything I've shown before. So I'll open it up for questions. So I'm still waiting for questions. Again, I apologize at the beginning here. I actually forgot to unmute myself, so rookie mistake. I apologize. Okay. So one question: how do you know when a power spectrum analysis is appropriate? How do I know? I just rely on the algorithm itself. So, and like I said, I use it to actually trace back variability. You'd be amazed sometimes. One of the first times I used some of these, again, was at a paper mill, but actually we trace variability on the basis weight on the paper machine product to some strange ancillary type of control loop that you would never have thought it would be contributing to the overall basis weight variability. And what I also do sometimes is that if I think that this one upstream variable or interacting variable is contributing, what we tend to do is that we tend to put that one in manual mode. If the cycle disappears and we know it's a contributor, and obviously the cause and effect, by putting a manual, you collect data on the effect side, whatever you think is being affected. If that disappears, we know there's a causality there, and therefore we know where the variability is coming from. Another question: what software tool do you use to calculate? There's a different type of software. What I use is the 𝗦𝗡𝗙 toolkit, which is an Emerson product, and I use that to do the 𝗦𝗡𝗙 toolkit. Comprises of 3 components. They're very imaginatively named. One called collect, one called analyze, and one called tuner. And what you were seeing there, I was using analyze to do my analysis and do my power spectrum analysis. Like I said, it is a Emerson product. So another specific question here: what are the delta V tools for power spectrum analysis? Again, the 𝗦𝗡𝗙 toolkit is available for obviously proper licensing, proper fees. It is available in the delta V for those of you who have delta V. So it actually it is part of the install discs, and if it's not, it can be installed, and with the proper licensing, you can activate it and obviously use it. Another question: what software do you use the data collection? Was it delta V or third-party software? I think I answered that. Again, the 𝗦𝗡𝗙 toolkit. You can go back, you can Google that, and you'll see it'll take you to the Emerson, or go to go to our website, Lakeside Controls, type in search 𝗩𝗡𝗙𝗘𝗘, and it'll bring you right to the proper data sheet. So what did you change on the steam pressure controller to remove the oscillation? Excellent question. What I actually did there, I actually retuned it. It was not tuned properly. And so by tuning it, by changing the tuning parameters, it was I eliminated the cycle, and therefore all those effects. And what actually it was, because the steam system is so interactive. So when one actually oscillated, it caused the other ones to oscillate and caused all the other one in between to oscillate. The whole system was just oscillating and dancing, but with itself right now, kind of like the Billy Idol song there, "Dancing with Myself." And so I actually not just had to retune that one, but that was the major source, but I actually had to retune a whole bunch of other steam pressures and steam differential pressure controllers to calm the whole system down. And that all contributed to the elimination of that cycle. These are great questions. So I'm sure there must be more questions out there. So again, I will wait. So I'll wait for another minute or two. Oh, there we go. I got another one. I guess to reframe my question, what leads to the up to the point where you might do a power spectrum analysis? A variation in process parameters is discovered in a continuous process. I actually, when I collect data, sometimes I'll look at it on the time series. It depends on what I'm looking for. But if I'm starting to do some optimization, or a lot of times say, well, we know this is oscillating here. We're having swings. Can you tell us? Can you help us out? Why is this happening? And so I would take a look. Okay, so you got a reactor temperature swing. All right. So what could be affecting that temperature? I'll start collecting data on that temperature, on that composition, whatever, and then whatever I can imagine in my head, whatever else can affect it, and therefore I'll collect all that data set as one. Do my analysis, say, okay, this is a cycle I see here on that reactor temperature. And then suddenly I see, oh, there's a level cycling over here. It seems pretty far, but it obviously seems to be contributing to it. And I see the same cycle. And so therefore I would say, all right, now if I were to eliminate that cycle upstream, so that level controller, which is what we think too far upstream, but is obviously contributing to it, I would put that in manual mode, collect the data again, and then see if there's any change in the power spectrum. If there is a change, obviously that upstream loop contributes to the cycling. So that's how I would use it. So another question, can we use the 𝗩𝗡𝗙𝗢𝗘 toolkit install on 𝗪𝗚V for tuning third-party device via OPC? And the answer is, I believe so, yes, so long as the OPC database has all the appropriate data points. You can connect to that OPC database and be able to collect data. You can also always use offline data. It's very, very good. I use it all the time. I can read in CSV files. So customers will actually send me data sets, and I could just import it right into Analyze. So it doesn't have to be right on 𝗪𝗚V. And so another question. So was the PID controllers being reduced and reset time being increased or detuned to avoid oscillation? I believe it was not tuned properly at all. And I can't remember now if it was, I think I did increase the gain, and actually, believe it or not, I think I actually decreased the integral quite a bit. And it actually was able to track a lot better and be a lot more stable. So another one is, thanks for showing this. It's so interesting. I wish I had known about this method years ago when fighting in an old thermal power plant. That's awesome. Yeah. It's never too late to learn. Appreciate the comment. Thank you. another comment is, what are the limitations of the FFT? Are there any cases where you want to provide an accurate power spectrum? And the answer is yes. So if you remember when I talk about fast Fourier transforms, it requires a 2 to the power n number of samples. So as I said, so if I were to have 65,536 samples, which is 2 to the power 16, it would use that all those samples. But if I had 65,535 samples, one less, it would only use the first 32,768 samples. I would lose a lot of the information. And so if I have an oddball number of samples, I will use a full Fourier transform to make sure that it captures all the information available. And as I said, the downside of a full Fourier is that computationally a lot more intensive, and it's a lot slower. I've had data sets, like I said, that were like 100,000, 200,000 data points, and you're doing that on 10 data sets. It takes a while. It may take 30, 40, 50 seconds before you're actually able to calculate them all. So that's the downside of the full Fourier, and the downside of the fast Fourier, it needs 2 to the n power number of samples. No, this is great. Keep the questions coming. Appreciate it. So another question. The paper machine's output spectrum shows oscillation at different periods, but you left them unchanged because the period did not line up with moisture. So those machines' oscillations have no impact on paper quality? Another very, very good question. So the other two variables that I was showing you, the top liner machine chest and filler liner or base liner machine chest, had different oscillations. And they were probably, it's like layers of onions. So once you attack and you eliminate the first dominant cycle, the one I just showed, the other ones may pop up, or maybe there's no effect. Who knows? And what you would do then is it's like layers of onions. So we remove that one dominant cycle, and perhaps the other one will start then showing themselves more because they're not overshadowed by that dominant cycle. And what I would do again, as I said before, to really kind of do a proof of cause and effect, what I would do is put the one of those in manual. I would put the top machine chest, let's say in manual mode, collect data for half a day. Yes, it would require constant operator intervention to maintain that level, not go dry. But then you would collect that data, and then you would compare it to the one before and say, okay, did the variability get reduced? Is that cycle still there, or is it gone? Perhaps it's worthwhile addressing. I did retune those two level controllers, by the way, and they do have some. The variability was actually quite reduced, but they're also experiencing some valve issues between those two. So there was still some work to be done. But I did eliminate some of those cycles on those two tank levels as well. Keep those questions coming. Appreciate them. Now, as I mentioned, this is being recorded, so and obviously with the muted part at the beginning. But so you will be able to refer to these. I'll be able to send you the link to this recorded webinar. And as always, if you have any questions, you're more than welcome to reach out to me. Like I say, email is probably the best. So I'll just pause here for another bit to see if there's any more questions. And while I'm doing that, maybe I'll just see where we are. You could see here, there we go. So it's look more and more like a square wave. It's not perfect. We would have to add here a few more infinite harmonics to be able to get a perfect square wave, but you could see that we're slowly getting there. All right, I'll pause for another minute here till 11:52. See if you have any more questions. Otherwise, we will wrap it up. All right. Well, I want to thank you very much. Oh, I got another question here. What tool can you suggest to figure out correlation between two parameters? Well, that would be between two parameters. I would use a cross correlation function. And cross correlation, it's a very statistical, commonly used function, and to be able to see if there's any kind of degree of correlation between two variables. Actually, the 𝗦𝗙𝗡𝗙 toolkit is a pretty cool tool where you can actually load in multiple data sets, and it'll give you a matrix of correlation, color-coded matrix based on if it's, I think if it turns dark blue is highly correlated, if it's dark red is highly anti-correlated, and shades of pink if it's slightly less correlated. So it's actually pretty cool. It can give you some good quick look at what to see if there's any kind of cause and effect. So the cross correlation is the answer. So it is 11:53 Eastern Standard Time. As I said, you're more than welcome to contact me. As I said before, when I was pointing towards my hair, I actually got my hair cut for you guys, so that's why I'm turning the camera on. I didn't want to scare you too much. Thank you very much for attending. Be very careful. For those of you in Southern Ontario, tomorrow it's going to be nasty, nasty weather, and be very safe. And we'll see you on March 24th. Catch me if you can. Thank you very much. Have yourself a good day.